Today, we're going to dive into one of the absolute cornerstones of data science, simple linear regression. We're going to see how a humble, straight line can give us a surprisingly powerful peek into the future.
So can a simple straight line really help us predict what's coming next? It sounds way too simple to be true, right? Well, as we're about to see, the answer is a big, emphatic yes. This one idea is the bedrock for so much in the world of data, so let's unpack it.
Okay, let's make this real. Picture a company. They've got years and years of sales data. They know exactly what they sold last month, last quarter, and last year. So how can they use all that history to make a really good, educated guess about what they're going to sell next month? This is the classic problem that linear regression was born to solve.
To solve that company's problem, or really any prediction problem, the very first step is always the same. We have to see the data. We need to visualize it, to look for a pattern, a trend, some kind of relationship between what we know and what we're trying to figure out.
To do that, we've got to get our key terms straight. First, you have the dependent variable. This is our target, the thing we want to predict. In our example, that's sales, and we always put it on the vertical y-axis. Then you have the independent variable on the horizontal x-axis. This is the thing we're using to make the prediction, in this case, time. We're basically asking, how does sales change as time goes on?
So once we plot all our sales data over time, what we'll probably see is a cloud of dots scattered across the chart. So how do we make sense of that cloud? This is where the next big idea comes in. We summarize all of that messy complexity with one single elegant tool: a straight line.
This line is called the regression line, and you can think of it as the average trend of all our data points. It's the general direction the data is heading. If sales are generally going up, the line will point up. If they're going down, the line will follow. It's a super simple visual summary of the whole story.
And every single straight line has its own simple recipe. Now, this might give you a flashback to math class, but stick with me. It's y equals mx plus c. This little equation is the engine of our prediction model. M tells us the slope, you know how steep the line is, and c is the intercept, which is just the spot where the line hits that vertical y-axis.
And this brings us to the most critical question of all. I mean, you could draw a nearly infinite number of straight lines through that cloud of data points. So how do we find the one single absolute best one?
This is really the central problem that linear regression is designed to solve. We can't just eyeball it and say, that one looks pretty good. We need a precise mathematical way to define what best actually means. And here's the secret to defining best. The best line is the one that is, on average, the closest to every single one of our data points. We measure this closeness with something called error. For each data point, the error is just the vertical distance between the actual dot and the prediction made by our line. The solution has a fancy name, the least squares method. What we do is calculate the error for every single point, we square each of those errors, and then we add them all up. Now, why do we square them? Well, it makes sure all the errors are positive, and it really penalizes the bigger errors. The method then finds the one unique line where this total sum of squared errors is as tiny as it can possibly be. That's it. That's our official line of best fit. Okay, that's enough theory. Let's see how this all works with a real-world example from our source material. We're going to take this whole process and use it to make an actual, concrete prediction. So check this out. Here we have a classic data set from data science. On one side, we've got head size in cubic centimeters. On the other, brain weight in grams. The big question is, can we actually predict a person's brain weight just by knowing the size of their head? And the process is always the same. We gather our data, with x being head size and y being brain weight. Then, we unleash the least squares method to calculate the best possible slope, m, and intercept, c. Once we have those two numbers, we can build our final predictive equation.
And here it is. After the computer crunches all the numbers, this is the equation it gives us. But what do these numbers actually mean? Well, that slope, 0.263, tells us that for every 1 cubic centimeter increase in head size, our model predicts a 0.263 gram increase in brain weight. The intercept, 325.57, is just our starting point. This formula has now captured the specific relationship between these two variables. And now for the payoff, the whole reason we did this. We can use this equation to make predictions. Let's say we find someone with a head size of exactly 4,000 cubic centimeters. We just plug that value into our equation, do the math, and out comes our prediction, a brain weight of about 1,378 grams. Just like that, we made a specific, data-driven prediction.
Now, this example is just the tip of the iceberg. The same powerful logic of fitting a line to data is used, well, pretty much everywhere in almost any industry you can imagine. Let's zoom out and see just how important this really is.
I mean, seriously, businesses use it every single day to evaluate sales trends. Finance uses it to try and forecast stock prices or economic growth. Scientists depend on it to analyze experimental data. Marketing departments use it to figure out if their expensive ad campaigns are actually boosting sales. It's a true workhorse of data analysis.
So we've seen how simple linear regression can take a messy cloud of data and turn it into a powerful predictive tool. By finding that one perfect line of best fit, we can make some pretty solid educated guesses about the future. But this amazing tool has its limits. It assumes the relationship is a straight line. And the fascinating next question is, what happens when the real world isn't so simple? What do we do when the data curves and bends? Well, that's a story for another explainer.